have the knowledge to do, but some of them will certainly become easier as we learn other things. 3 is one of those. As we get to the end of, get through chapter 4, one like 3 will be a little easier. All right? Now, some of you, I think, were thrown off a little bit by this whole dt. Now, what's d theta dt mean? With respect to t. So another way of writing that is what? What's another way of writing d theta over dt? Theta prime, right? Theta prime of t, right? Theta prime. So that's another way of writing that. Now, you're going to see today, we're going to do some talk about parametric equations in chapter 4, and you see where this Leibniz notation becomes important, okay? But you notice it's in all of the answers. What that means is theta prime is in all of these answers. There's a theta prime in all the answers, okay? So just kind of tuck that away here for later when we get to that. Now it says, which expression gives the rate at which the slope is changing? So that would be, in other words, aren't they asking kind of for m prime? Right? If m is slope, they're asking for m prime. That's what they're asking for. Well, before you can find m prime, what do you need? An equation for m, right? So what we're looking for here is an equation that has m in it. And okay, now let's set this up. Okay, and you also look at all your answers, and they got all these trig values in here. Well, what we have a line going through the origin, sort of. Okay, we got a line going through the origin that is rotating, and here's the angle theta. Well, if you look at this, slope would be rise over run. Okay, right? The slope of this line is rise over run. Well, what do you know in trig language, and Kelsey just said it, that's this over this. Tangent of that angle. Tangent of theta. And that is actually what tangent is. Tangent of theta actually does represent the slope of the hypotenuse on that triangle. Because it's rise over run. So setting up that equation. Now that's one of the things we're going to do in one of the sections in chapter 4. We're going to do a lot of work on finding rates of things where we have to set up the equation. So once we've done that, we will be better at doing a problem like this than we are right now. All right, well, if that's m, then what's m prime? Secant squared theta. See, and that's where everybody wants to stop, and that's where you'd be wrong. Now, that might be enough to answer the question, but what do we need to tack on? The derivative of the inside. What are we doing the derivative with respect to here? T, right? We're doing the derivative with respect to t, not theta. So it's like when we do an x. If we're doing derivative with respect to x, we don't write x prime because that'd be dx over dx. If we were doing the derivative of theta here with respect to theta, if we were doing dm over d theta, then we would not tack on a theta prime because that'd just be 1. But that's not what we're doing. We're doing the rate with respect to t. All right? So m and theta are both in terms of t. So m prime, we do the derivative, we got to tack on the derivative inside, which would be the theta prime. It's like we do the y prime, where we tack on the y primes with implicit differentiation. That's what it is. Okay, so we've got a couple of examples of things we'll do in chapter 4 where we will do implicit differentiation quite a bit. That's what you have to do. Well, which one of those choices is that? That's d right here. Secant squared would be 1 over cosine squared, and the d theta dt is the theta prime. Okay, so again, everything that was in that question, we have the capability to understand. We just have never put anything like that together and set that up like that, which makes it tricky. All right, 13. If the graph of this has an inflection point at -1, then what is the value of k? Anybody got an answer for this one? A. Let me pull up the chart real quick. Okay, so inflection point, a possible inflection point is when the second derivative is 0, right? Now, it's only truly an inflection point if we get a change in concavity, right? Okay, so we'd be looking for the second derivative here. So we're looking for this, that'd be 4x. What would this be? Kx negative 1. So that'd be negative kx to the negative 2. And then the second derivative would be 4 plus 2kx to the negative 3. And we want to know, we want that to be 0. Oh, when x, that's right, when x is negative 1. So that means we can plug that in. So I would rewrite this. I would put the x on the bottom, like so. And then we want negative 1 in here. So that would make negative 1. So 4 minus 2k would equal 0. So 4 would equal 2k. Did I do something wrong? Because I'm getting 2. I thought I heard people saying A. Right. I think it must be positive. Yeah. I'm just wondering. Well, let's go. I got it right here. What number was that? 13? 13 is it's 2. So anyway, so if you got negative 2, maybe you missed a negative up here when you did your derivative or something. Right. K is a constant, and since it's multiplied here, right, it'd be like having 3x to the negative 2. You just bring the negative 2 down in front, which would be negative 6. You just multiply it by what's there. So when we bring that down in front, we just multiply it by the k. Yeah. K is just a constant, and we're finding that value. Okay. Now before we do 9, let me before I leave this one, let me make a comment here. Now, remember, all we did there was find when the second derivative is 0. That's not enough to know we have an inflection point, right? We'd have to have a change of concavity, all that. But they told us that it's an inflection point. And so we can assume that a good place to look is when the second derivative is 0. Now I want to talk about 15 a little bit here in a minute, and talk about how the second derivative being 0 might not be the whole story either on inflection points and concavity and stuff like that. But okay, so let's go to 9. Whoops. All right. So, okay, now what was number 9? Okay, so what'd you do here? Okay, well, this was kind of what I was talking about earlier with the implicit. The equation of tangent line, we need y equals the slope, x minus 5. They give us the point, right? So we got all that. All we need is a slope, so we need y prime. So that would just be 2x plus, anybody? Yeah, 2y prime, answer your own question. And then 0, right? And so then all we have to do now is subtract the 2x. Got it? And then divide by 2, that'd be gone, so we just get negative x over y. Did I do that right? And then plug in those points. So that'd be 5/12. Negative 5 over negative 12. Now from there, I got some algebra to do. But I think it ends up being C. Is that right? It's C, I think. In other words, at this point, I would distribute the 5/12 through, maybe multiply everything by 12 to get a fraction out of there. Get my x's and y's on one side, whatever. But yeah, at that point, you just go from there. So implicit differentiation. Again, a classic kind of an AP test question where they check several different things. They want to see you do an implicit differentiation. They want to make sure you know how to do equation of a tangent line, and then a little algebra thrown in to boot. right? To get it worded or to get the answer written the way they have it. All right, I want to look at 15, and then if anybody else has another one, we would have time to maybe do one more. But there's something about 15 I really want to talk about, because as we get into the end of doing derivative problems, we need to make sure that we start to bring in some of these technicalities that we've left off when we were first learning about it. When we were first learning the chart and concave up and concave down, we left off a lot of kind of technicalities. We would talk about how, oh, let's assume that the curve is nice and smooth and it's not, no sharp points and none of that kind of stuff. Well, now we got to start thinking about maybe those are involved here. And so let's take a look at our chart. And there might be some things we need to fix on this chart. For example, we said here that a local max, a local min, or a flat spot means that f prime is 0. Well, what about this situation? Yeah, f prime's not 0 there. So we probably ought to have this in here as well. So f prime could be undefined, right? And we've also said, what would you do if you wanted to find out when f is increasing? If you want to find out when f is increasing, what do? You would find when f prime is positive. Well, how do you find when f prime is positive? We would do a number line. If we don't have our calculators especially, we would do a number line. Now, what do you put on the number line? You put on when f prime is 0. And then you check in between. Well, now we're going to need to put on that number line also when f prime is undefined. In other words, not stationary points. We're going to need to do, what were they called? No. Stationary points is when f prime is 0. Critical points are when f prime is 0 or undefined. So we're going to have to take in those considerations. Now, that also applies to concavity. How do we tell if f is concave up? Well, if f prime is increasing. How do we tell if f prime is increasing? If f double prime is positive. How do we tell if f double prime is positive? Do a number line. What do we put on the number line? Well, we got to check when f double prime is 0, but we also have to check when f double prime is undefined. Because what if you have a situation like this? What if you have that kind of a graph? Does the concavity change at 0? Does the concavity change at x equals 0? Yeah, it's concave up before 0, and it's concave down after 0. Is there an inflection point at 0? No, there's no point where the concavity changes. You can't have an inflection point if there is no point, right? And so a possible inflection point when this is 0, but you could still have a change in concavity. So if the question, now this gets to number 15. Question 15 wants to know, where is f concave down? Right? Well, it's concave down when f double prime is negative. How do you find when f double prime is negative? Well, check when f double prime is 0 and do a number line. But we also have to consider maybe when f double prime is undefined, because we could get a situation like this. We could get a change in concavity without there being an inflection point. And so we have to consider that. So these are some of the kind of technicalities that we have to now take into account, because they're going to start showing up. Oops. They're going to start showing up a lot more than they did before. And that's exactly what's going to happen here. So it says, where is this concave down? And it's no calculator. So what you need to do is you need to find when f double prime is negative. That's what we need. Well, a great place to look is when f double prime is 0. That's where we usually start thinking. And then later we would think, oh, you know what, we better check about undefined as well. So let's start by doing that. So let's do the derivative. Did anybody get an answer for this one, by the way? E? No, so Kelsey, you said E. Now, how did you do this? Is this what you did? With f double prime? Okay, all right, so that's the right attack. So I would first write this way. We talked about that yesterday. Now, maybe you want to do a quotient rule, you can, but when there's a 2 up on top all by itself, I wouldn't. But anyway, so if we bring that negative down in front, and we can't forget what? We got to kick out the derivative of the inside, which is -1. Oh yeah, and that's to the -2 power. So the -1, the -2 would be a positive. So we would end up getting this for our f prime. Right? God, I can't have a tough time with that for some reason. Okay? So it's 4 minus x to the -2. Okay. So then f double prime, we would bring that down again and get -4, 4 minus x to the -3, and then we'd kick out our -1 again, the derivative of the inside. So we'd end up with +4, 4 minus x to the -3. Now it would be easier if we flip that back to the bottom, like so. Okay. So now, typically what we would want to do is we would want to say, where does this equal 0? Well, where does a fraction ever equal 0? When the top is 0, right? And we're going to use that a lot here as our functions get messier here in chapter 4. When the derivative or any fraction is 0, when the top is 0, well, this top will never be 0. So the derivative, the second derivative here will never be 0. But now where will be undefined? At 4, right here, because you get a 0 on the bottom. So what we find when we have fractions for derivatives and we want to do number lines, we end up checking when the top is 0 and we end up checking when the bottom is 0 because we get both parts of that, when it's 0 and when it's undefined. So it's at 4. So right away that makes you think you're probably looking at one of these here. So I think you end up getting it right, yeah. So what we would do is we would put 4 on a number line. But there is no inflection point here. It's important to understand. We're looking at the situation like I described earlier. There is no inflection point here because this function is undefined at 4. Go back to the original function. It's undefined at 4. There is no point on this graph at 4. It's an asymptote, okay, which kind of fits in with the work we were doing with limits earlier too. So anyway, you put a 3 in here, you're going to get a positive. Put a 5 in here, you're going to get a negative. So concave down to the right of 4 when x is greater. Okay, so all these things we did with the chart before, there's going to be some of these technicalities, some of these things are going to pop up that we've got to be able to deal with. All right, one more we have time for if somebody's got another. If not, that's okay. All right, too late. Get your notes out. Oh, okay. Which one? 18. Just snuck it in time. 18. dy dx, which means the derivative of y with respect to x, so it's another name for y prime. So this would be a product rule. So derivative of x is 1, ln of x squared left alone, plus x left alone, and then this is going to be a mess, so I'm going to put parentheses. Derivative of that, we bring the 2 down in front, leave the ln x alone, then to the first, and then times the 1 over x. I think I did that right. And so I got a term here, and I got a term here that's all multiplication, so these parentheses don't really matter, so this x and this x could cancel. So I think I'm going to get ln x all squared plus 2 ln x, I think. And it looks to me like they factored out an ln x. So maybe I would do that here. Take out an ln x, I'd get ln x plus 2, which would be c. All right. So obviously we've been doing some where we talked about showing work. There's some graphing ones where there wouldn't be any work to show, where you're matching some graphs. Clearly one like this, you're going to have some stuff on it. Okay? All right. So let's move ahead because I do have kind of an activity worksheet for your assignment here, and I want to give you a decent amount of time to work on that today. So let's get your notes out and let's move on into what we're going to talk about here in chapter 4. Everybody logged in? I only have 11 people logged in. And I know that because our presenter is not logged in. And our presenter is Ryan Clark. Oh. All right. Go to the graph screen and parametric mode is where we're going to go here in a little bit. Okay, so you'll need your calculators here in a minute, but we're going to write some stuff down here first. Or you can write some of this down. I'll have it up on the screen tomorrow again. The thing down here in the bottom with the line, don't worry about that. Down here in the bottom right corner, don't need to worry about that. But we're going to be talking about parametric equations. Okay? Parametric equation. And that's what we did when we did the line and the range. And parametric equations are when we had one equation for the x, which is the horizontal movement, and one equation for the y, which was the vertical movement. And I guess I should say horizontal position and vertical position. Okay, and when we graphed that, we were checking to see if the line and the range are met, where they were on the path that they were traveling. Remember, the lines were their paths, and where they were at a certain time was told by the parametric equation. So parametric equations are great for showing motion. And if we have motion, we're going to have velocity and we're going to have acceleration, and so that's going to fit in with derivatives. All right, and so this is section 4.4 in your book. We're kind of going out of order here a little bit. We're going to do 4.4, then we're going to go 4.3, and then I think 4.5, and then we'll do a quiz over all three of them. They're all different sections. They cover totally different things. The only thing they have in common is the derivative is involved. Okay, and that's what all of chapter 4 is. Right? All of chapter 4 is just different uses for derivative. So we're going to extend what we learned about parametric equations when we did the line and the ranger, and we're going to involve now the derivative aspects of it, because it involves motion. And if there's motion, there's rates of change. But when you have two-dimensional motion, you have a variety of different rates of change. Okay? And that's why we've got these three things up here. Now, the first one should be the simplest of those. And that is, we break down the horizontal and the vertical individually as one-dimensional motion. Now, here's what I mean. So, before, when we first learned about motion and velocity and stuff, we talked about Bismarck, and we talked about east and west of Bismarck. And so if I'm going this way, I'm east, so I have a positive velocity, and if I'm going this way, I have a negative velocity, and if I get west of Bismarck, then I have a negative position. If I'm east of Bismarck, I have a positive position. But we didn't talk about any north and south. It was all just east and west. It was all just one dimension, right? And so if I'm going east of Bismarck and I get over here and I stop to turn around, right? What was my velocity? 0, right? And then I come back to the west, right? So I had a positive velocity and then changed to a negative velocity, so at some point I had to have a 0 velocity. I had to stop. Now, if you're driving in your car and you make a U-turn, do you ever really have to stop? Your eastward or whatever would stop, right? You know what I mean? Because now all of a sudden you get into a U-turn, now you're getting into two dimensions. Now you're bringing in some north-south as well, right? So that's kind of what's happening here when we start talking about parametrics. So far, we've just been talking about a function. We've just been talking about like altitude, like vertical, or horizontal, like a particle on the x-axis. That's just one-dimensional motion. So when we say the particle stops to turn around, right? So if I make a U-turn my car may never actually stop, but at some point my eastward movement stopped, right? So my eastward velocity would be 0, but I'd have a little bit of north-south velocity in the middle of that U-turn. So that's the stuff we're going to be talking about here. So we're breaking this up. So if I've got an x equation, which is the horizontal position, and a y equation, which is the vertical position, then x prime would be my horizontal velocity, and y prime would be my vertical velocity. So when would my car actually be stopped? When they're both 0, right? If your horizontal movement has stopped and your vertical movement is stopped, then you're stopped, right? Then the car is not moving. But if it's moving diagonally, it's got some horizontal movement and it's got some vertical movement that's making it go diagonal, right? And so that's what parametric equations do for us, is they let us have two-dimensional motion, but we're going to break it up into those two components, the horizontal and the vertical. All right, so those are the first important ones you need to know. Now, x prime and y prime. Now, number 2, here's where it gets really interesting. So let's say I'm driving on a curvy road, and I guess I can't do it on the board here because I'm recording. So let's say I'm driving on a curvy road like so. And I'm driving along here. Okay? Well, and let's say north is up here. Okay? So when I get right to here, and I'm moving this way, right? When I get right to here, what can you tell me? Y prime of t right here would be 0, right? And what about, let's say that right here the road is going straight north. Then you would know that x prime would be 0 right there. All of your movement is vertical at that point, be a vertical tangent, right? X prime would be 0. Now, what can you tell me about the slope here? The slope of the path, the slope of the road is 0. What about the slope here? Undefined, right? So here, the y prime matches that, but here it's not. Okay? Well, if this would be my x, I mean, if I was going to put an axis on this, right, this would be my x-axis and this would be my y-axis. So this slope here would be, this slope we're talking about here would be dy over dx. There would be no t involved in this, right? This slope here would be dy over dx. Whoops. Does it make sense why this would be undefined? Because x prime is kind of like the dx, and y prime is kind of like the dy. And so what you see here is this formula. The slope of the path is dy over dx. So now we got to be careful with our notation, because if we just call this y prime, the vertical velocity, this would also be called y prime. But they're two different things. This is the derivative of y with respect to x. This is a derivative of y with respect to t, like miles per hour, minute, feet per second, or something like that. So here's the formula for the slope of the path that the movement is on. It's the y prime of t divided by the x prime of t. Okay? So we can find the slope of the path by taking our two derivatives and dividing them. And you're going to get to do that on your worksheet. Okay? So that's a formula you've got to know. We've got to know that. So what gets interesting about this is our derivative gets a lot more specific about what it means. We can't just say, well, y prime is speed, or y prime is velocity, or y prime is rate of change, or whatever. It's with respect to what? So with respect to t, we're talking about horizontal vertical velocity because of the time element. The slope of the path, though, is not the rate. And I think we saw that in the Lion and the Ranger. We knew the Lion here had a slope of 1/3. But that wasn't how fast he was moving, right? That wasn't how fast he was moving. That was just the slope of his path. He was moving 0.3 miles per minute this way and 0.1 miles per minute this way. The slope of his path was 1/3, but that was not the rate he was traveling. And that brings me to the third formula. How fast is the object moving on the path? Well, we got to use both of these velocities, and that's what we did with the Lion, if you remember. That's why we broke down the Lion and the Ranger to the minute. We said the Lion was going 0.3 miles every minute here and 0.1 miles every minute here. So where was he really going? Well, we need the hypotenuse. Well, to get the hypotenuse, you do this squared plus this squared, do the square root of it. Well, this was his horizontal velocity because that was miles per minute. And this was his vertical velocity, which is miles per minute. It turns out we squared the horizontal and vertical velocities, added them up, did the square root. That gave us the hypotenuse. That was his actual speed, which was different than the slope of the path. Slope of the path is the y over the x. The speed is the Pythagorean theorem on the hypotenuse. Okay? So I hope in looking back on the Lion and the Ranger, you see all these different elements of the problem. Okay? And they all involve the derivative. And they all come from these original x and y equations. All right. So now we got to just get comfortable using those. So Ryan. Yes, it did. Some guys will do anything to get out of it. All right. Brianna Miller. All right. Thank you. Oh, hers. I was just going to say thank you for being responsible and having yours charged, but I see you plugged in. All right. So let's go into your. Let's go into the menu to graph. Yeah, graph entry. And everybody's going to do this for the activity we're going to be doing here in a little bit. So parametric. Now you might still have your Lion and Ranger in there. I don't know. Oh, we probably need to delete. Probably need to delete that one that's in there. I thought you did. Maybe you didn't hit the enter. Now hit the enter. There you go. Okay, now so we're going to go into our parametrics. Now some of you may have Lion and Ranger still in there, but she doesn't. That's good. So here's the one I want to do. I want to graph this. Oh shoot. Okay, that's all right. I forgot I didn't rewrite. Okay, we're gonna do two different ones. Okay, the first one I want you to do is x equals t and y equals sine of t. Okay, so let's do that. Let's leave it at that right there. Let's just leave it the way it is. Now, what's that look like? Sine graph. Anybody surprised by that? Why would this be the sine graph? Yeah, I mean, the equation x equals t tells us those two are interchangeable, right? If x equals t, then those two are the same. So I could replace this t right here with an x, and I'd get y equals sine x. Because this is the x-axis, this is the y-axis, so this is the graph y equals sine x. Matter of fact, it's a cool little quick way in parametric mode to do a normal regular graph that you'd like to do. You just let x equal t. I think I talked about that actually before when we were doing this, but let x equal t, and then let y equal whatever the graph you want to do, except put a t in instead of an x. And here you go. Now, let's go ahead and change our window just a little bit, Bree. Let's go to, let's not see so much of that x and y. So let's go in our settings and let's go, let's go -1. Let's go to about 12. That's fine. And then our y, let's go about -2 to 2. Okay. All right, and we only went from 0 to 2 pi on our t, right? So here we go. So let's trace here just a little bit on this. This is the blue person, okay? The blue person is walking along, and let's type a 0. And so we start there. Now type a 1. And so let's say this is minutes, and so t is a 1. So 1 minute later, we're there. And then type a 2. And 2 minutes later, we're there. Oh, we don't want that. Let's see if we can get rid of that. Because we're going to do some other stuff. There you go. All right. And so, all right, and so at 2 we're there, and then at 3, type in a 3, and at 3 we're there. So we're just walking along on this nice curved path. Okay, so now go back into your entry area, so we get just a nice sine curve here. All right, and now let's do x equals t squared and y equals sine of t squared. Anybody have any guesses of what this is going to look like? What do you mean by stretched out? What do you mean by longer? Stretched horizontally? Think about that, what I said a minute ago about that substitution thing. If x is equal to t squared,
That's going to be the same thing.
yeah, doesn't it? If x is equal to t squared, doesn't that mean we can replace t squared with x and we get y equals sine x? And that's exactly what that means. And so if we go onto our graph and see what Bree's got for us, there's the red graph. Now you can see below here the blue graph. So it is the same except what? This is why I said, what do you mean by stretched out? It's not really stretched out, it just goes along. Right? It goes farther. Now remember, this is just a picture of the path. Right? There's motion, just think of the trail around Kearney. And you got people walking and biking and stuff going on the trail, right? But the trail doesn't move and the trail doesn't change. So this is our path. And we've got motion on the path. Now, these two equations that I gave you, and go ahead and highlight those and get those out of there. Just click on them and then you can hit delete. So this one is the red. I should have done that in red, actually. This is the red one over here, okay? And this is the blue guy over here. These are two different parametric equations. So this is another powerful thing about parametric equations. They can show us the actual motion on the path. When we just write y equals sine x, that's just the path. Parametrics tell us where points are at certain times on the path. So we have a red person and a blue person. So now let's check them out. So same path. So we go in here and Bree, let's go to trace again. And let's trace, okay? So here's the blue guy at 3. Now hit the up arrow. And there's the red guy. And look when the red guy is there. Hit a 3, type a 3. There's the red guy at 3. So the blue guy's here. The red guy's here. It's kind of like me and Ryan in a race, and I'm the red guy. And after 3 minutes, I'd be way up there, and he'd be way back here. So go on the blue guy, arrow up. Yeah, see, at 6, the blue guy's here. So you see why the blue graph stopped right there? Because we went from 0 to 6.28, right? So the blue graph stopped. The red guy at 6.28 gets a lot farther, right? So so it's two different objects on the same path. Now, if we wanted to do so, go back to our formulas, and you see why we need these different formulas. Because two different equations, same path, but we're going to have, each of these has a different vertical and horizontal velocity. They have a different x and y equation, so they're going to have different x primes and y primes. The speed's definitely going to be different of those two, right? The red guy's going much faster. What about the slope of the path? The slope of the path is the same, but at different times, right? In other words, if we do at t equals 3, what's the slope of the path? Well, it depends which guy you're talking about, because they'll be at different places on the path, so the slope will be different. But at the same x and y coordinates, yes, the slope would be the same. So let's just do a couple of quick calculations here, and then I'm going to let you do some work on your own on this kind of a thing. So let's go in here for the blue guy, and let's say, what was his horizontal velocity at t equals 3? Let's do that for both of them. What was their horizontal velocity at t equals 3? And this is no calculator now. I shouldn't need a calculator here. Look at those formulas we wrote down. What would be the horizontal velocity at t equals 3? Write down what you think. Now remember, they're at different places, right? They're at different places. Not that that matters to you when you're calculating this, but okay, somebody got one for the blue guy? What's his horizontal velocity is always 1, isn't it? Because horizontal velocity is x prime, right, with respect to t. So his horizontal velocity is always 1. What about this guy? Red guy is 6, right? Because his horizontal velocity is 2t, right? X prime. X prime is horizontal velocity. X prime of t is horizontal velocity. So at 3, x prime would be 6. Okay? What if I said, when does blue guy stop going up? When's the first time that the blue guy stops going up or going north? What would be? Now see, you're thinking, okay. So you're saying the blue guy stops going up when t is 1.57 whatever pi halves. Is that going to be the same thing over here? Okay, no. Now, why did you get that? So you were answering this question, right? When does blue guy stop going up is like saying, when does his vertical movement stop? Well, just like we were talking about before. Movement stops when the velocity is 0. We're talking about going up. We're talking about the vertical. So we would answer the question, when is y prime 0? Well, when does sine equal 0? Excuse me, cosine, right? Y prime. So y prime would be cosine. So when does cosine t equal 0? We would solve that equation. And that would be at pi halves. That'd be the first time. So t equals 1.57. We'll trace there in a minute. Okay? What about this guy? When does this guy stop going up? Isn't it the same question? When does y prime equal 0? That's true of any particle in any problem we ever do. In parametric equations, when does it stop going up means when y prime is 0. When does it stop going horizontally means when x prime is 0, right? It's the same question. So what do you need? You need y prime. Well, what would y prime be? 2t cosine. Now, we need our calculators for that. So everybody, let's get on our calculators and do that. Bree, you can do it for us here on the calculator screen. So we would need to calculate, we would want to solve, we would want to solve 2t. Now, we got to make sure to put a time sign right here. Anytime you got t and then a cosine, you need a time sign between there or it'll get all messed up. 2t cosine t squared. Of course, we could have told part of this. Equals 0. Whenever we solve the cosine equation, what else did we say we probably needed? I wouldn't hit enter yet. We better do the vertical bar, right? Now, we don't know for sure when we're looking, but we know we start at 0 and then maybe, so let's go from 0 to, I don't know, just so we don't get a whole bunch of answers. Let's go like 0 to 5 or something. Oop, got to be outside. Yeah, outside the parentheses. So let's go 0 to 5. Let's include them. So let's include the 0. Because one of them is going to be 0, right? We can see because of the 2t, right? So that's interesting. Oh. Still hit control there. Hit control there. I wonder why it gave us those. Okay, 1.253, we'll use that one. And then keep going. And then it says, and this is greater than 0, or t equals 0. Okay, and there's another 4 point. Okay, what's that mean, the one at 0? What is that? Because we didn't get that on the other one. Go back to your graph. If we were to trace the movement of this particle, what happens to that particle, the red particle at time 0? It's actually stopped, right? It's actually stopped because both its derivative and its horizontal and its vertical velocity are 0 at that time. The blue particle, that's not true. It's moving at time 0. Okay, but this one's actually stopped. So that's one time. But then what was the other one? 1.2 something? Trace on the red. Trace on the red at 1.2. I can't remember what it was. 1.25 or something. Somewhere in there. Okay, there it is, right up there. That's where we expect. And then on the blue one, let's trace at 1.57. And that's where we are right there, right? And so we found it exactly. Okay, so those are some of the things you're going to be doing on your worksheet today. Okay, so that's just a little bit of an introduction here to get us started with parametric equations. You're going to have the rest of the time here to work on this worksheet. So basically your assignment is this. Excuse me. To finish this worksheet, okay, for tomorrow. Now you'll get a lot of it done in class. Maybe all of it. And then in the packet, make sure, first of all, you get the rest of that section done. Okay, that first section of multiple choice, no calculator. Then go into the next section and try to get at least 3 of the circled ones. Right? The next section in the packet. Try to get at least 3 more of those done. So all of those circled ones in the first section, which you should have basically had for today. And then try to get a few more done. And again, it's not bad to get ahead. Eventually we'll do all the circled problems. So you look at your schedule and you think you're going to have some time and want to get ahead on some of those, that's not a bad idea. Okay, you can go ahead and get together and work on this for the rest of the time.